Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can design a program counter using a behavioral model first in a system Verilog program, and then we are going to see the same using a VHDL program. So program counter is actually a register, a special kind of a register. So this is a system Verilog program first, and here we have defined a module named PC, which is going to be program counter. It has these two outputs, PC and next PC of 8 bits, and then it has inputs which are power, clock, branch enable, stop enable, and then it has an 8-bit input as well, which is going to be the branch PC, which is going to be that branch address. So this is a program counter where we can implement a branch logic as well. And after that, here we have defined the PC as a reg, and this PC we are going to use inside this always block, always add positive clock, and then we are going to say assign next PC to PC. So this is actually a register we have implemented inside this PC. So this is sequential logic. That's why we have non-blocking assignment here. This one, this arrow and equal to. And since our PC is going to have some combinational logic as well, so this is the next part. And here we have defined next PC as reg because we are going to determine what is going to be the next value of our PC, next address of our PC. And here we are saying inside always block that check power input signal, stop enable, branch enable, or PC. So we are going to use here PC as input to next PC as well, although it is defined as an output. That's why we are placing this thing here. And then after that we are checking here first of all power. So if power is going to be 1, then we are going to follow this logic, and if power is going to be 0, no power, then we are going to say next PC is going to be all zeros. This else statement we are saying here. But here in the logic we are showing now if power is equal to 1, what it is going to do, it is going to check stop enable. If we want to stop our PC at a specific address, we can use this, and we are going to say okay, in that case next PC is going to be the PC, the same PC where we have stopped our program at that moment. And then we are going to say if stop enable is 0, this else statement we are going to say then check branch enable. So if branch enable is true, then we are going to say next PC address is going to be the branch address, or otherwise if there is no branch enable, we are going to say increase PC by 1, and that is going to be our next PC's value. So check here we are using a blocking statement here because here we are implementing the combinational logic, blocking, blocking assignment, all these. Here we were using the non-blocking for the register. And then we are going to end this, and else we already know. So this is our complete program. So I have compiled this program already. Let me show you first the test bench. So this is going to be our test bench, and here we are saying module test bench. The outputs we have defined here as buyer, the inputs, all inputs as reg, the way we do it. After that, here we are calling that module PC, and we are mapping all these outputs and inputs using the positioning. And after that, inside this initial block, we are saying start from clock equal to 1, and after that we are saying power is equal to 0, stop enable is equal to 0, branch enable is equal to 0. Check this case, branch PC we can give a value. Then next we are going to say make power equal to 0, stop enable equal to 0, branch enable equal to 1. Let's see what is the case. This way we can try all the 8 combinations. So here for example we have this branch enable equal to 1, stop enable equal to 1, power equal to 1. What is going to happen at this PC address, the branch address? So after that we are going to say always after 5 nanoseconds invert the value of clocks. This is the way we run the clock and end module. So this is our complete program. We can either use this line always to implement the clock logic and this line combined, or outside this initial block we can define another initial block and we are going to set using this for ever loop as well. So these are two ways. So my code is already compiled. Let's try to run this. Simulate. Let's drag all these signals here. Run simulation. And here we can see our output. So here the power is 0, here the power is becoming 1. Same way here branch enable. We can see here branch enable is coming and here we have branch PC. So at next clock cycle we are going to have our PC as this 05. This is way it is going to work. So you can check it later. This is the way our PC is going to behave. Let's close this simulation and try another way using this behavioral model. So these are procedural assignments. So now we are going to implement the same logic using the continuous assignments. So comment out these lines and come here, uncomment these lines. So this is the same logic. Here we are checking, we are saying here branch enable. If it is going to be true, give this branch PC to next PC, otherwise this increment like this and give that. And first of all we are going to check the power. If power is going to be 0, give PC this one. If power is going to be 1, then check if stop enable is going to be 1 also, then give this PC to next PC, otherwise do this. So this is the same logic which we are implementing above in these 4 lines. But this is continuous assignment. The result is going to be a bit different than this one, but the logic is going to be same. The way the output waves are going to show, those are going to be different a little bit because continuous and procedural assignments just behave a little differently in simulations. Go to Testbench, simulate. Let's see the inputs and outputs. So we can see here that within the same clock cycle, once our branch enable is going to happen, it is going to update the PC like this. So it is not going to wait for the next clock cycle the way it was behaving using the procedural assignment. So this is just a little bit different, but the logic is same, the way it is going to behave. So you can understand it later. Let's end simulation. Go to design file again. And this is actually behavioral model. Now I am going to modify this code so that we can implement this behavioral model with a structural model. So skip out these lines, and I am going to just add some variables here which are going to be new wires, so that later if we want to implement this code design as a structural model we can do it. So include these wires, three wires: increment PC, temporary PC1, temporary PC0. So here this last line we are implementing here PC plus 1. We are saying increment PC is going to be this one, and then after that this one. Second last line we are implementing here. Temporary PC is going to be implementing this line. Then third line this one. Stop enable we are checking here. Temporary PC1, and then later this line, the first line. But if you are going to check this line, this is going to be implemented by a incrementer. Using structural design we can create another module named increment, and we can implement this same way. These three lines are three muxes, 2 to 1 muxes, 8-bit muxes. So using that module mux we can implement these three code lines using a structural model, which I am not going to do here, but this is the way we can actually modify our behavioral model to implement it as a structural model. So save this, compile, and let's run the simulations. Drag here, and we are going to see the same output and input combinations. Let's close simulation. So this is the way we can implement a program counter design using system Verilog. And now I am going to flip over to our VHDL project so that we can see how we can implement the same stuff using a VHDL design. So this is our VHDL design file. Here we have declared an entity PC which is going to have this PC as in out power input clock input branch PC input branch enable input stop enable input, and then next PC as in out as well. This I am going to tell you later why we are not defining it as out, and instead why we are using here in out for these two cases. But let's go further. This is the architecture, and here we are implementing our register 8-bit D flop. We are going to say inside this process block. Let's skip out these lines, these signals we don't need right now. We are saying okay, check the clock. If clock is going to be 1, give this next PC to PC. This is what we are going to always have in our program counter. Next, here we are going to implement the combinational logic inside this process, and then we are going to say Okay, check the input power, stop enable, input branch enable, and PC. We are going to use as an input as well because we are going to use it here to assign it to next PC. So after that, we are going to implement the same logic. If power is going to be 1, then check if stop enable is also going to be 1, then next PC is going to be PC. Don't increment PC. Otherwise, if stop enable is not applied, check if branch enable is equal to 1, then next PC is going to be branch PC. Else, if branch enable is going to be 0, then PC is going to get incremented by 1, and this is going to be our next PC. So after that, we are going to end these if statements here and end process at the end. So this is our complete program. Let's save this. So this is the same logic we are implementing here using VHDL. Compile this, test bench, simulate. So this is the test bench which we are using here for this program simulation. And here we have defined this test bench, which is entity, and inside this architecture, we are using this PC program counter entity as a component. And here we have defined this PC as in out. The same way, all the ports, input and output ports, and then after that, we are using these signals to map the inputs and outputs inside this begin block. We are calling here our main entity of our design PC, and this is the way we are going to map the inputs and outputs. And after that, in this process block, what we are saying is we are going to design our clock is going to be 1, and after 5 nanoseconds it is going to become 0, and this is the way we are going to loop this. And then after that, within this process block, we are making first of all power equal to 0, stop enable equal to 0, branch enable equal to 0, and after that we are making here branch enable equal to 1. Here we are making stop enable equal to 1, and same way we are going to try different combinations, all 8 combinations, and we are giving here branch PC address as well. We are changing those, and this is our end of the architecture, and this is our complete test bench code. So let's run this simulation. Drag these inputs and outputs to this wave window, run, and here we are going to see the same input and output combinations. So here we are making power equal to 1, and here we are saying this next, this is our branch PC. Branch PC is going to be our next PC, and here we are making this PC equal to 0, 5, this branch PC. So you can understand it later. Let's end the simulation, and I am going to show you how we can implement the same design using another approach so that we can convert this model later into a structural model. This way we can't implement it. Let's skip out these lines, and let's include these lines. This is just another way of implementing the same logic. So here we are saying the same thing. We are saying if power is equal to 0, give this value 0002 to next PC. Otherwise, check stop enable. If it is going to be 1, give PC equal to next PC. Otherwise, we are saying check branch enable. If it is going to be 1, give this branch PC address to next PC. Otherwise, increment PC by 1, and this is going to be our next PC. Same logic we are applying here. We can compile and run this code as well, and it is going to work the same way. But now I am going to show you this same logic we can implement in another way, so that later we can use this code to model this design as a structural model. And we are going to include these three signals for that: increment PC, temporary PC1, temporary PC0, and let's use these here. So here what we are doing is we are making first of all this PC plus 1 equal to increment PC, and then later we are using this first signal which we have defined, and we are implementing this line. So we are checking this branch PC, this branch enable, and we are using this line here. We are using this line here, and we are making this line equal to temporary PC1, and finally this first line we are making it equal to next PC like this. So this is our complete program, but like I said earlier, this is just a increment circuit which we can define another entity and place this logic inside that entity. This is just another 2 to 1 mux 8-bit. We can implement this line by using a mux, this line by using a mux, this line by using a mux. And this way we can convert this code into a structural model. But right now I am not going to do that. Let's save it. Let's compile this and see the output. Drag these all ports here, run this, and we are going to see the same input and output combinations. So this is the way actually guys we can implement a program counter with branch logic using system Verilog code and a VHDL code as well. So thank you guys. I hope you guys have enjoyed this video. Have fun.